In this video, I will go over how to model this triangular wave pattern in Python. I'll do it with an intuitive walkthrough rather than a specific formula, because there is a formula that estimates the pattern of the triangular wave. Now, I'll actually go over that at the end of the video, but in this video, I want to go over a more intuitive way to code it out. Now, in practice, you probably wouldn't do it this way because it's just not as efficient, but it's a more simpler way to do it, and you can kind of see what's happening instead, rather than using some obscure formula. So the reason you might want to do this is, let's say that you have a specific loop, let's say a for loop, which is what we're going to be doing now, and you want to vary a parameter in this sort of shape. You want it to start off with like a minimum value and then go over to a maximum value and then back down and then repeat in that way. You can do it this way. And this plot here that I've got is just an example triangular wave. The blue one is the triangular wave, and then the orange is an example of the wavelength, which we're going to use in constructing this model. And the wavelength is just the time it takes, or the amount of x points that it takes to complete one cycle. So to start with a minimum value and then go back down to the minimum, or in the same way, the wavelength can be defined at any point. So the wavelength is the same up here as well. If you want to start off with the maximum value, the distance between these peaks or the maximum values is the same as the distance between the minimum values. So essentially that's the wavelength that we're going to define. So we want to define some values first off, and we can start off with a maximum and minimum value. So the minimum value we can set to something, let's just say 5, and the maximum value we'll set to, let's say 20 for this example. We also want to set the wavelength, so let's just put the wavelength as 10 in our case. So that is the distance that it takes for one cycle, and essentially what we're going to use is we're going to use half of the wavelength, and half of the wavelength is the distance or the time that it takes to complete one whole increase. So let's say that you start with the minimum value. The half wavelength is the x time that it takes to get to the top, and then in the same way another half wavelength, and you'll get back down to the bottom again. So we're going to need that parameter. So we're going to say half wavelength is wavelength over 2. We're also going to need an initial parameter value. So the way that I'll construct this model, we can either begin at the minimum or we can begin at the maximum. If you want to begin it somewhere in the middle, it's easier to just model it using the formula. And I'll just quickly show you the formula to show you what I mean. This is the Wikipedia page for waveform, and it shows 4 different wave types. We're doing the triangular pattern here. The formula is quite complex. Like if you look at the triangular wave one, this is the formula to model it, and we'll model it with this at the end of the video, but I want to go over a more intuitive way first. So this is what I mean when I'm talking about the formula. Anyways, so we can start off with either the minimum or the maximum value, and the parameter that we're going to vary, we're just going to call it parameter. And parameter is going to be, the value of it is related to this y-axis here. So the parameter value is what we're going to change, and the parameter value is what is going to follow this triangular wave pattern. So we start off with, let's just start off with the minimum value first up. And then we want to calculate the step. And the step is the movement in the parameter with one iteration. So if I just construct the for loop here, and let's say it goes from 1 to 100, the wavelength is in reference to this for loop. So with a wavelength of 10, what we're going to be saying in this model is we're going to be saying that we want the parameter to complete one cycle in 10 iterations. So if we start off with the minimum value, we want it to get back down to the minimum value in 10 iterations. And then in the same way, to construct this, we want the parameter to get from the minimum value to the maximum value in 5 iterations, which is half of the wavelength. And then back down, it'll take another 5 iterations, which is half the wavelength. And the reason for this is that the slope upwards and the slope downwards is exactly the same. So we can use this half wavelength to go from down to up and then up to down. So it's in reference to these iterations. So the step is going to be the step for one iteration, which is going to be constant in terms of the size, although the direction is going to be different. So if we're going on this uphill portion here, we want the step to be positive. And then if we're going on this downhill portion here, we want the step to be negative. But it's going to be the same in magnitude. The actual value of it is going to be the same. The absolute value, I should say. So what I'm going to do is I'm actually going to code up this for loop here. And that way you'll see what I mean in terms of the step if you don't know it yet. So what we're going to do is we're going to go parameter is equal to parameter plus step. And a different way to write this is just parameter plus equals step. Those two lines are equivalent, they mean the same thing. So this is adding step to the parameter with each iteration. So what we want is we want it to take 1/2 wavelength before we change the sign of the step. And when I say change the sign, I don't mean sign as in like, the trigonometric functions. I mean sign as in plus to negative and negative to plus. Positive, I mean negative to positive and positive to negative. So we want it to take, essentially it will take 1/2 a wavelength to change the sign. Because if we start at iteration 1 over here, or really it's iteration 0 if we're starting at the minimum value, and then in 5 steps, we're going to reach the top here. So 1, 2, 3, 4, 5, roughly. So we've reached the top here, and that's when we change the sign at iteration 5. So we go 1, 2, 3, 4, 5, and then we change the sign again. So essentially every multiple of 1/2 a wavelength, we change the sign. That's what we want to design the step. When we write the variable for the formula for the step here, that's the way we want to design it. So now what we're going to write here is we're going to write an if statement that will test whether or not we are at a multiple of 5. And the way we can do this is write if, I'll just write it out first. And then step is equal to step times -1. So what this tests for here is it's saying that if I modulus 1/2 wavelength is equal to 0. And that'll find all the i's that are multiple of 5, because you can imagine that, well, 1/2 wavelength is equal to 5. So if I is equal to 5, 5 modulus 5 is 0. So is 10 modulus 5 and 15 modulus 5 and so on. But then obviously something like 3, 3 modulus 5, that's not equal to 0. So that's why that works. And then what we're doing here is we're just reversing the sign of the step. So every 1/2 wavelength, every multiple of 1/2 wavelength, we're going to be reversing the sign, because we're starting here, or we're starting here for that matter, because we will define it such that, we'll construct it such that we can start at the maximum value as well. So every multiple of 5, in this case, which is a 1/2 wavelength, we need to reverse the sign, because if we start here, we get a multiple of 5, we're up here, we reverse the sign. Another multiple of 5, we're down here, we need to reverse the sign. And then equivalently, this statement can be written as step times equals -1. That just means the same thing. Alright, so that's the for loop essentially. And what we want to also do is we want to keep track of the parameter values. because we're going to plot it afterwards so you can see the shape of this. So to keep track of it, we can just create a list and say param list, or we can say parameter values. And we start with just one point or one parameter value there, which is just the initial parameter value, which is equal to minimum value. And then with each iteration, we just append the parameter value there. So we change it. We test if we need to switch the step around. And then we append the change. So we're going to get a list of all the parameter values here. We're going to get a list of all these values as we change them, as we add step to it. So actually we need to define what step is, but this is going to be the format for the for loop. So all we need to do to finish this is just define step. And the way to do that, it's actually pretty straightforward. So firstly, I'll just define it for the upwards direction, which is going to be the same as the absolute value of the downwards direction anyways. So the way to do that, I'll just write it out here. And it's that simple. So the maximum value minus the minimum value, that's just going to be the difference between the two. So that's the distance that we need to cover essentially. And then we divide that by half wavelength, which is how many iterations we want to take to cover that distance. So if we have if this distance between here and here is 15, then we want to cover that in half of the wavelength, which is 5. So we've got a step size of 3. And if we go up by 3 and then go up by 3 and then go up by 3, 5 times we've covered the distance, and then we can just repeat that on the way down. So that's all you've got to do to write down the step. And what we want to do is this is going to be the initial step essentially. And the reason that the step, we call it the initial step, is because we're changing the sign of it with every half wavelength. So we need to make sure that the initial step is like the same sign that we want essentially. So if we start with a minimum value, we want the initial step to have a positive direction, a positive sign, because we're going upwards. And if we start with the maximum value, we want the initial sign to be negative because we're going to be going downwards. And the way to test that is we can just use Boolean operators. So if we write something here and we say initial direction is equal to, I'll just write it out here first. And then all we do is just multiply this by initial direction. So what we're doing here is we're going to multiply the step by 1 or -1 essentially. If we multiply by 1, the step is going to be positive because this value is always going to be positive here because maximum value is greater than minimum value. But essentially, if this is 1, step is going to be positive and we're going upwards. If it's -1, step is going to be negative and we're going downwards. So the absolute value of step won't change, it'll just be the direction. So essentially we want initial direction to be 1 if we begin at the minimum value, and we want initial direction to be -1 if we begin at the maximum value. Because if we begin at the minimum value, the initial direction is going to be positive, and if we begin at the maximum value, the initial direction is going to be negative. And that's what we're doing here, is we're just setting initial direction is 1 if we begin at the minimum value, otherwise it's -1. And the only other situation we have is if the parameter begins at the maximum value, because that's the way we've constructed this model. So that's the way that works, and that's literally all we have to do. So I'm just going to run this, and then I'm going to plot what comes out. Did I even run it? I think I did run it. There you go. There's the graph, and what I've got here is I've got the blue line is the triangular wave, and that's what follows the parameter values here. And then the green line is the maximum value, and the orange line is the minimum value. So we can see that it goes from minimum to maximum to minimum to maximum and so on. So it goes between these two lines. If we begin with the maximum value instead, we can see that we start with the maximum value, and because the direction is -1 now, and thus the step is negative, we start going downwards first. And this will work for most cases, or actually it works for any minimum value and maximum value that you want. The wavelength has to be even, because when we're dividing by 2, we get the half wavelength, and the half wavelength will only mean something in this case if it's a whole value, because half wavelength defines how many iterations we need to get from the minimum to the maximum and from the maximum to the minimum. So it only makes sense if we have a whole number of iterations, and the only way we can have a whole number of iterations in the half wavelength is if we have an even value of the wavelength. So like, I'll show you what I mean. If we put 9 in this case, it messes up and it goes downwards. But if we put it like 12, it works fine. So we've got a negative value here. Let's say we have 2 negative values there. That works out as well. Let's say we increase this to 300 points. Oh, hang on. Have to run everything. There you go, it works. If we increase the wavelength, you can see that these get further apart. Essentially, the slope gets less steep, and the reason for that is it's just taking longer to complete a cycle. So that makes sense. If we increase the wavelength to 100, then it looks like that. But essentially, that is the triangular wave. That is an intuitive way to code the triangular wave, and what we're going to do now is just compare it to this formula here for the triangular wave. And the way we can do this is just using NumPy. So we import NumPy, and then t. So t is going to be the independent variable in this case. T is the same as, what do we have? T is the same as I in this case, essentially. We can use the linspace function here. Let's say 0 to 100 and 101 points. So t is going to be now a vector, essentially, an array. And that's why we're importing NumPy. It's just an easier way to do this. So then the triangular wave, what we're going to solve for is y here. And that is 2 times a. And we'll define these parameters in a second. Times NumPy.arcsine. I think these are the right formulas for arcsine and sine. I'll check if they're not, but they should be. Alright, let's just make sure I got this correct. So we have 2 times a over pi times arcsine of sine of 2 times pi times t minus phi. That's what the phi is, that's just this symbol here. And then divide by lambda. Yeah, that should be right. So let's just define the parameters here. And if you want to look at the parameters more, they say what they are here. So t is time, lambda is wavelength, A is amplitude, and then phi is phase. So if you want to look at these more, they're on the Wikipedia page here. So let's just put some random values in this case. So we can go A is equal to 3, lambda is equal to 4, let's say. You know, just something like that. And obviously we define t here. So, alright, it looks like it worked fine. So let's just plot this. And yeah, you can see a triangular wave pattern over here. So you can play around with some of these values here for the variables. For example, if we want to reach, like get a more constant, not constant, if we want to make it closer to our situation here, we can note that the amplitude is a lot bigger in ours. So we can increase the amplitude here to, let's say, 20. Maybe that'll work. Yeah, so it goes closer. And if we want it even closer, let's say 25. And yeah, it's getting closer and closer essentially for that one. Then you can play around with more of these, and I don't know too much about what these mean. I mean, the amplitude, I know that means the distance between this value here and then this value here. So like if we increase the amplitude to 10, then you know the highest value here is 10 and the lowest value is -10, or close to that anyways. And then phi, that's the phase. I know that's to do with like some translation for it. So if we have a phase of 0, we start at the point 0. And let's say we have a phase of 10. We start at a -2.5 in that case. So I'm not exactly sure how the phase works. You can look at it if you're interested by just clicking on this. But anyways, this is the official, you know, formula for calculating or for estimating the triangular wave. Because you can see that some of these points here, and then down here, they're not, you know, they have this little movement here that's not really consistent with a triangular wave pattern. And that's just because it's estimating it, you know, it's not perfect. We've got some trigonometric functions here, so you're going to guess that it probably has some of that effect, and it's not going to be like a perfect triangular wave pattern. But anyways, that is how to code up a triangular wave pattern intuitively, and then also to use just the, you know, classic formula for it. And there's other ones as well, the sine wave, sawtooth wave, which kind of looks like this. I might do that at some point, try to code these up intuitively, in a sort of, you know, similar way to coding this up with a for loop and all that. But anyways, I hope that helped.